In this video, I'd like to introduce electrophilic aromatic substitution. And this video is just going to be a very brief primer on the subject. I'm not going to delve into any of the details of any particular reaction that falls under this general umbrella. But this is a very common reaction mechanism, and it's something that you'll encounter at the undergraduate level all the way up to a professional setting, so medicinal chemistry or process design at a pharmaceutical company. And the general scheme is actually very simple. We start with an aromatic hydrocarbon. Now, I'm going to use benzene as an example, but you could use any other aromatic molecule. Toluene, as long as it's basically an aromatic hydrocarbon. It could be a polycyclic aromatic, it could be monocyclic. Any aromatic hydrocarbon will work in this reaction. So I've chosen benzene as an example. And our aromatic molecule is going to react with an electrophile. And electrophile I've denoted by capital E plus. And let's just spell this. Electrophile. And in organic chemistry, you're going to encounter this suffix very commonly, phile. And it's from the Latin word phyla, or the Greek word philos, which means loving or love, or basically attracted to. So electrophile basically means it is attracted to electrons. And the reason that the electrophile is attracted to electrons is because it's very electropositive. It is electron deficient. And so it's going to be drawn to and in fact attacked by any source of electrons in theory. Now benzene actually is a good source of electrons because it has 6 pi electrons. I'll actually redraw them in blue so that it's clear. So here are our 6 pi electrons in benzene. Now the difficulty is that benzene is an aromatic molecule, and for an electrophilic attack to occur, it actually has to disrupt and break the aromaticity of benzene. So we'll draw the attack and then we'll explain. So the electrophile gets attacked by benzene, and we generate what is called a sigma complex. Like this, which is a carbocation. And you can see that now we have 4 pi electrons in the ring, and we've actually disrupted the aromaticity of benzene. So this is a high energy intermediate. And typically, benzene and aromatic hydrocarbons don't like to break their aromaticity like this because you're going from a low energy state to a very much higher energy state. So typically, an attack like this doesn't happen easily. And what we do in electrophilic aromatic substitution is we generate a very, very strong electrophile, sufficiently strong and sufficiently electron poor that a stable molecule like benzene will still attack it. And so typically the electrophiles that we encounter under this reaction umbrella are very strong electrophiles. And we actually have to generate a very strong electrophile in situ using one synthetic measure or another. But once we generate a strong enough electrophile, we generate this sigma complex cation. And the final step is simply rearomatization via deprotonation. And what we get is our substituted benzene. Okay, we functionalized benzene. And this is the importance of this reaction mechanism because you can take an inert hydrocarbon like benzene and functionalize it. So you can add something to the benzene molecule that may be synthetically of interest. And so this is a very common reaction that you're going to see in the chemical literature, and it's a very useful one for building up molecular complexity. I just want to have a brief look at this sigma complex. And if we consider this intermediate, we can see actually that there is some resonance stabilization here. And since there's a cation, we can draw a couple of resonance contributors. So we can draw the cation here. And we can draw that same cation here. So the cation is delocalized in the sigma complex intermediate. which has a stabilizing effect. Now, it's still not as stable as the resonance stabilized starting material. And so this actually goes through a high energy intermediate. And the way we can think about this is if we draw a reaction coordinate diagram like so, where we have energy like this and the reaction like this. I'll label this starting material as A, our sigma complex intermediate is B, and our product is C. What you basically see is you have a reaction that goes through a high energy intermediate and then comes down to the product. So here's C, here's A, and here's B. And it has to go through a high energy intermediate. Now, if the electrophile is very reactive, then if you consider the benzene and the electrophile taken together, we can imagine maybe a higher energy state like this. So the higher the reactivity of the electrophile, the less ground it has to cover in terms of energy here. So a very reactive electrophile is going to help this reaction proceed. But generally, we have to go through a high energy intermediate. So one of the things we have to do is, number one, we need a good electrophile, something which really is very electron deficient and is looking for a pair of electrons. And number two is, ideally, you want the aromatic to be electron rich. So the more electron rich the aromatic, the more quickly this reaction will typically proceed. So there's a lot of ways to make an aromatic compound like benzene more electron rich. You can add an electron donating substituent, such as a methyl group, and this donates electrons inductively. You can also add something like a methoxy, and this will donate electrons actually by resonance. So you can envision something like this. And we now have considerable electron density at the ortho position. And this is one of the reasons that a methoxy is a very strong ortho or para director. And I'll make a separate video about ortho, meta, and para direction in another video series. For now, we're just focusing on electrophilic aromatic substitution. And so this is the general scheme. And it's worthwhile to remember that no matter what reaction we go over in future videos, they are all going to follow this reaction pathway right here. And so this is the general mechanism that you're going to have to know. And if you know this general mechanism, you'll be able to do the mechanism of any of the specific examples that we're going to cover.